Hello viewers, we're now taking you through the story for A-Level Physics Paper 1, and this video I'm going to go through the topic of calorimetry and in particular specific latent heat. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we proceed, let's first look at the course outline of this paper. So physics paper 1 is divided into 3 parts. The first part is mechanics, where 4 questions come from these topics. Second part is heat, where 3 questions come from these topics. And the third part is modern physics, where 3 questions come from these topics. So, and for modern physics, we already completed all the parts, the calculation bit of it. And for heat, we have done part 1, part 2, and we are going to part 3, which is calorimetry and in particular specific latent heat. So we're interested in calculations, but notes which are complete are available in this book called Mastering A-Level Physics Paper 1. It has clear notes, worked examples, and trial questions in mechanics, heat, and modern physics. So the worked examples in this book are the very questions we shall go through on this platform. So if you need a copy of this book, contact the author on any of these 2 contacts. And a complete set of physics has 3 books. There is Physics Paper 1, Physics Paper 2, and Physics Topical Question Bank. Then for principal mathematics, there are also 3 books: Math Paper 1, Math Paper 2, and Topical Question Bank. For subsidiary mathematics, it is only 1 book. And the rest are for O-Level. There is O-Level Physics Question Bank, Topical, O-Level Math Question Bank, Topical, and O-Level Physics Notes. So for any of the copies, contact the author on any of these 2 contacts. So just start our topic of calorimetry, and we're interested in specific latent heat of fusion and vaporization. So we shall first look at the terms we shall be using in this video. Remember, our interest is the calculation part of it, but before we do the calculations, we need some of the theoretical part. So let's first begin with the terms which will be frequently used in this video. One is latent heat. So latent heat is the quantity of heat lost or gained. So it can be heat lost or heat gained during the change of state at constant temperature. So the key word which is very important is this word constant temperature. So each time you see the word latent heat, just know temperature has to be constant. And the SI unit is joule. So latent heat Q can be given by the formula that Q is equal to ml. So m is the mass of the substance and L is the specific latent heat of the substance. It can be specific latent heat of fusion or specific latent heat of vaporization, depending on the change of state. Is it from liquid to gas or from liquid to solid? So now what about specific latent heat? So specific latent heat is the heat required to convert 1 kilogram mass of substance into another state at constant temperature. So constant temperature is the keyword for the word latent, and 1 kilogram is the keyword for the word specific. Remember, in part A, in the definition for latent heat, it was just any mass, but when they add on the word specific, then the mass has to be 1 kilogram. So the SI unit for specific latent heat is joules per kilogram. What about specific latent heat of fusion? So now they have added the word fusion. So it is specific latent heat of fusion. We shall say that this is the quantity of heat required to change 1 kilogram mass of a substance from solid state to liquid state without changing temperature. So like I said, latent, the keyword is temperature has to be constant. Specific, the keyword is mass has to be 1 kilogram. Now when there is fusion, it implies that the change of state has to be from solid to liquid. Solid to liquid, that is latent heat of fusion, or liquid to solid. So here, when they don't put there the word fusion, it implies that it is any change of state. It can be solid to liquid or liquid to gas. But when they put the word fusion, it must be solid and liquid. What about if they put the word vaporization? Vaporization, the keywords will be the same, specific will be the same, 1 kilogram, latent will be the same, change in temperature is constant, there is no change in temperature. Then, but vaporization, now the change of state has to be liquid and gas. So for fusion, change in state is solid and liquid. For vaporization, change in state is liquid and gas. Latent means temperature doesn't change. Specific means mass has to be 1 kilogram. So let's first look at a graph showing the variation of temperature of steam being cooled with time. So we get steam and we cool it. How will the graph be? So that is how the graph will be. This is 100. Remember, steam is at 100 degrees Celsius. So when you cool it, it is first constant, meaning it is changing from steam to condensed water. That means there is latent heat at this point. Then along BC, from here to here, the water is cooling from 100 degrees Celsius to 0 degrees Celsius. And when it reaches here, it is constant, meaning there is a change of state. So water is freezing, is changing to ice up to point D. And from point D, it is ice. So that graph is beneficial to help us in the calculations. That is why I have brought it here. Remember, whatever we do here, the theory part we do here is to help us answer the calculation bit of it. So that was cooling steam. What about variation of temperature of solid being heated with time? So first graph was cooling, now it is heating. So here at first it was solid, and this is the initial temperature, but when it reaches the melting point, it changes to liquid. So at this point, there is solid plus liquid coexisting. So here it is being changed, it is changing. That is why temperature is constant. So each time there is a change of state, temperature has to be constant. So it was initially solid, now it will change to liquid. And from this point onwards, it is now a liquid. So it will be heated until boiling point. When it reaches boiling point, it will now be vapor. That is why temperature is constant. So liquid is changing to vapor. So these graphs are vital because they will help us in the calculations. And now it is time to see how helpful they can be. So if theta 1 is the initial temperature and theta 2 is the melting point, and theta 3 is the boiling point of the liquid, the total heat gained by the solid can be illustrated as follows. So when given a question to calculate, you don't need to draw a graph. What you need is to make a simple sketch of what happens. So this is shown with the aid of block diagrams. So the first one was solid at initial temperature, which is θ1. And that solid, the temperature keeps on increasing up to melting point, which is θ2. So there is a change in temperature. Then from here to here, there is a change of state. It was solid, but now it is changing to liquid. Therefore, temperature does not change. So each time there is a change of state, temperature should not change. Therefore, as I draw your diagrams, ensure that. Now it is liquid. That liquid heated more, the temperature will increase up to boiling point θ3. At θ3, it needs to change to vapor, so temperature will not change. So θ3 will remain the same. Okay, so now we need to, how do you do the calculations? Each time there is a change in temperature, that means there is specific heat capacity. Therefore, it is MC change in temperature. But when there is no change in temperature, there is latent heat, specific latent heat. So from here to here, change in temperature is θ2 minus θ1, which is here. Then M, that is the mass of the solid, and CS is the specific capacity of the solid. That is from here to here. What about from here to here? Temperature is the same, therefore quantity of heat will be ml. So M is the mass of the solid and LF is the specific latent heat of fusion. Then from here to here, there is a change in temperature, so it will be MC change in temperature, which is MS, mass of solid, CL, which is specific heat capacity of the liquid, and change in temperature. Then from here to here, temperature is the same, meaning there is ML. So mass of the solid, specific latent heat of vaporization. So such diagrams are the ones which can help you to easily answer the calculation parts involving specific latent heat, and shall be using them more frequently. So after drawing this sketch, you can come at the total quantity of heat gained by the solid in the whole process is given by Q gain equal to this. So you keep on adding that plus that plus that plus that. So now it becomes easier after sketching. So we need to define the terms. Though this is mass of the solid, specific heat capacity of the solid, specific latent heat of fusion, specific heat capacity of molten liquid, specific latent heat of vaporization. So by conservation of energy, quantity of heat supplied by the electric heater is equal to the quantity of heat gained by the solid. So if the solid was being heated by an electric heater, then it implies that by conservation of energy, quantity of heat supplied will be equal to the quantity of heat gained by the solid. Therefore, you come and say that quantity of heat supplied by the electric heater is power times time. Power is IV, and multiplied by time to get the heat supplied, equal to this heat which was gained by the solid in the whole process. So I think you realize that now this equation becomes easier to quote if you illustrate. So note that this assumption made in the above expression is that there is no heat loss to the surroundings. So there are two cases while dealing with the calculations. One, it can be assumed that the heat loss to the surrounding is negligible. That is one part of the calculation. Or it can be assumed that the heat loss to the surrounding is significant. So while answering questions under latent heat, always find out should the heat loss to the surrounding be negligible or it should be significant, because both are dealt with differently, as we shall see in this video. So let us first start with the one part at a time. So we shall start with the part of questions which involve no heat loss to the surrounding. So these are the type of questions where it is assumed that the heat loss to the surrounding is negligible, can be neglected. Question 1 came from UNEB 2015 paper 1 question 5 and says a 600 watt electric heater is used to raise the temperature of a certain mass of water in a thermos flask from room temperature to 80 degrees Celsius. The same temperature rise is obtained when steam from a boiler is passed into an equal mass of water at room temperature in the same time. Note the word equal mass of water at room temperature and in the same time. If 16 grams of water were being evaporated every minute in the boiler, find the specific latent heat of vaporization of steam, assuming no heat losses. Assuming no heat losses. So mass of steam evaporated from the boiler per second will be given by that. Remember, here they said it is 16 grams of water is being evaporated every minute. But for us, we want per second. That is why we divide by 60. Divide the 16 by 60. Also, we want the mass to be in kilograms. Therefore, to convert grams to kilograms, we multiply by 10 to the power negative 3. That is why you see 16 times 10 to the power negative 3 to convert grams to kilograms, then divide by 60 to convert per minute to per second. That is why you see here the SI unit is kilogram per second. Okay. Therefore, the total rate of heat gained when using steam from the boiler is given by. So like I said, it is easier, it is better if you illustrate. So let us start by illustrating. Steam, as long as it is steam, just know that it is at 100 degrees Celsius. Unless it is a different kind of vapor, but steam, it has to be 100 degrees Celsius, which is the boiling point of water. So this is 100 degrees Celsius. Then changes, it is trying to change to liquid from steam, which is vapor, to liquid state. So this is now boiling water, but the temperature has not changed because there is a change of state. Then it reduces further to 80 degrees Celsius, which was given in the question. Therefore here, because there is no change in temperature, it is ml. Here there is change in temperature, it is mc, change in theta. So since the temperature rise is the same, it implies that the rate of heat gained when using steam from the boiler is equal to the rate of heat gained when using the electrical heater. So this heat from this plus this is that, and it is equal to this 600, which was the power of the heater. Then we shall substitute M here and here, then L, which they want, C. So specific capacity of water is a constant. That is why I'm putting here for 200. It is a constant and it will always be given. Theta 2 is this big temperature and theta 1 is this temperature. So there we have only one unknown. Our work is to simplify and then look for a way of making L the subject. When I do that, I'll come up with L being equal to this, and that will be the specific latent heat which they wanted. Then question 2 came from UNEB 2014 paper 1 question 7D and says a liquid of specific heat capacity this and specific latent heat of vaporization this is contained in a flask of heat capacity that at a temperature of 32 degrees Celsius an electric heater rated 1 kilowatt is immersed in 2.5 kilograms of the liquid and switched on for 12 minutes. Calculate the amount of liquid that boils off, given that boiling point of the liquid is 100. Now here it is now a different liquid, not water. That is why they have to give you the boiling point. So we shall not use 100, we shall use this boiling point which is given. But still, we have to make a sketch. So this is what was given. That is that. This one is here. And the mass is there. Then this one, heat capacity. I think you realize that this is small c, this is capital C, because capital C means heat capacity. The time is that, and the temperature, there is 32, and there is this 80. So let M be the amount of the liquid that boils off. So still we shall make an illustration. At first it was 32 degrees Celsius. The liquid was in a flask. Then on heating, it began boiling at 80 degrees Celsius. Now because this is boiling point, it means that it will now be converted to vapor, but the temperature will not change. Okay, so from here to here there is a change in temperature, so it will be MC change in temperature. But remember that we have two components. We have a flask and a liquid. Now a flask, it is C change in temperature because this C is heat capacity. Here for the liquid we have MC change in temperature because this small c is specific heat capacity. So in the previous video we looked at those two formulas, the formula of quantity of heat given heat capacity and the formula for quantity of heat given specific heat capacity. So I believe by now you are familiar with those formulas. Here there's no change in temperature, so it will be ML. Okay, now here what you need to realize is that the mass here of the liquid is M1. But here I'm putting there M. Why? Because from here to here, this mass is the entire liquid which was given. But from here to here, the mass I'm using is the mass which is vaporizing. That's why you said let M be the amount of liquid that boils off. So the mass that is vaporizing is that M. And if you look at the question, it is the mass they want. So after making an illustration, it is now easier to calculate. So let's begin the calculation. So by conservation of energy, electrical energy supplied is equal to heat gained by liquid and flask plus the latent heat gained. This is what we have seen in the illustration in the previous slide. So this is electrical energy supplied. This one is gained by the flask, gained by the liquid. This is the one which is vaporizing. So come and substitute for power. 1 kilowatt is 1000 watts. Time 12 minutes convert to seconds. Heat capacity is that. Change in temperature is that. Mass, specific capacity, change in temperature. Mass that boils off is unknown. Latent heat of vaporization is known. So we have one unknown now. So meaning we have to look for making it the subject. First we shall simplify. So this one gives this, the whole of this gives that. this gives this, and that gives that. Then simplify further and then make M the subject. Then question 3 came from UNEB 1996, paper 1, question 5C, and it says, an electrical heater rated 500 watts is immersed in a liquid of mass 2 kilograms, contained in a large thermos flask of heat capacity that, at 28 degrees Celsius, electric power is supplied to the heater for 10 minutes. If the specific heat capacity of the liquid is this, its specific latent heat of vaporization is this, and its boiling point is this, estimate the amount of liquid which boils off. Then state an assumption made in your calculation. So still even here, they want the amount of liquid which boils off. Should I first interpret the question by interpreting what was given? Power, this is mass, heat capacity, initial temperature, time, specific capacity, latent heat of vaporization, and final temperature, which is the boiling point. Then we have to illustrate. Illustrating is very, very vital as long as it comes to latent heat. So this is the initial. On further heating, the temperature increases to 78, which is the boiling point. Then it goes to vapor at the same temperature. So still we shall do like we did before for the flask and for the liquid, and here for the latent heat. So that during the sketch, we can easily now do the calculation. So by conservation of energy, electrical energy supplied is equal to heat gained by flask and liquid plus latent heat gained. Quote the formula, then substitute. After substituting, you simplify further and make M the subject, and that is what they wanted. The assumption is that all the heat supplied by the heater goes into raising the temperature of the liquid and flask. Then also the temperature of the flask does not change during vaporization of the liquid. Those are the assumptions. Then question 4 came from UNEB 2012, paper 1, question 5C, and it says, steam at 100 degrees Celsius is passed into a copper calorimeter of mass 150 grams, containing 340 grams of water at 15 degrees Celsius. So this is steam. It is passed into copper calorimeter of mass this, which has water of these grams. Should begin with that. This is done until the temperature of the calorimeter and its content is 71 degrees Celsius. Okay, so steam's temperature reduced to 71 and water's temperature increased to 71. Okay, if the mass of the calorimeter and its content is found to be 5 to 5 grams, calculate the specific latent heat of vaporization of water. So we're given a specific capacity of water and copper is this and that respectively. So here we have a copper calorimeter. Initially it has some water. Okay, then you pass in steam. Okay, but remember, as the steam goes here, it condenses and it also turns into water. That is why the mass here increases. So with that, let's go to the solution. One, we have to interpret what is given. So this is the mass of water alone, initially present, mass of the copper calorimeter, total mass after. So let M be the mass of condensed steam. It implies that the total mass is equal to mass of the copper calorimeter plus mass of water initially present plus mass of the condensed steam. Remember, this increase is because as the steam condensed, it turned into water. So what we shall do, we shall look for the value of M, and M will be that. Okay, now that we have got M, we can now go ahead and make our illustrations. So for steam, that is what we have. Initially it was steam, it goes to boiling water, then liquid at the final temperature, which is 71. What about calorimeter and water? It increased from 15 to 71. Therefore, by conservation of energy, heat lost by steam is equal to heat gained by calorimeter and water. So this is heat gained by heat lost by steam, and this is heat gained by water and calorimeter. So we shall substitute. This we already got M, L is what we want, M we already know it. This is the constant, change in temperature. Then here M1, C1, change in temperature, MW, CW, change in temperature. So it is only L which is the only unknown. Therefore, simplify further and make it the subject, and that is what they wanted. So I think you realize that when you illustrate, the calculation becomes easier. So each time you see the word latent heat, remember to illustrate. Okay, so I believe now you have got a good flavor of the questions where heat loss to the surrounding is assumed to be negligible. Now I want to look at questions where heat loss to the surrounding is significant. In other words, it is not negligible. So we shall start with question 1, which came from UNEB 2008 per 1 question 5C, and it says an appliance rated this evaporates 20 grams of water in 5 minutes. Find the heat loss if specific latent heat of vaporization is that. So you come and say that this is what was given, power is that, time 5 minutes, you convert to seconds, then the mass was grams, convert to kilograms, specific latent heat of vaporization. So by conservation of energy, we know that electrical energy supplied is equal to latent heat gained plus heat loss. I think you remember in the previous calculations we've been doing, where heat loss to the surrounding has been assumed to be negligible, we have not been adding this component. But now, when heat loss to the surrounding is significant, you must add on the heat loss. Okay. After adding it there, then you can proceed to substitute. Formula for electrical energy supplied is power times time. Latent heat gained is ml. Then heat loss to the surrounding is small h. So heat loss is small h, and then the rate of heat loss is capital H. So when you see that, when they just want heat loss, should be small h. When they want the rate of heat loss, it should be capital H, as we shall see in the question that follow. The next is to substitute for power, time, mass, specific latent heat, and this is the only unknown. So make it the subject, and that will be the answer they wanted. Then question 2 came from UNEB 2007 paper 1 question 6c and says, in an experiment to determine the specific latent heat of vaporization of a liquid using the continuous flow calorimeter, the following results were obtained. So these are the results. So we have the first voltage and the first current giving you this rate of mass collected. Then the second voltage, second set of current giving you that mass collected. So they said calculate the power of the heater required to evaporate 3 grams of water in 2 minutes. So here in this question, these are the grams evaporated in 300 seconds. And with this, these are the grams evaporated in 300 seconds. Now they want the power of the heater required to evaporate 3 grams of water in 2 minutes. So let capital H be the power loss to the surrounding. Like I told you, if it is just heat loss, it is small h to the surrounding. But if it is rate of heat loss to the surrounding, it should be capital H. Now this, because there is the word power, it means it is rate of heat loss. That is why I'm using capital H. Okay. So this is the power supplied is equal to latent heat plus heat rate of heat loss. So this is the rate of heat, latent heat, and this is the heat rate of heat loss, and this is the power or rate of energy supplied. So there are 2 sets. There is this and also this. This is for the first set and this is for the second set, because if you look at the question here, there are 2 sets. There is this set and also this set of V1, I1, M1, then V2, I2, M2. So when I subtract the 2, I'll come up with this. So this minus this, so this minus this gives you this. Then here this minus this gives you this part. And now when I subtract this, h's cancel. Okay, then I'll substitute for I2, V2, I1, V1, M1. So sorry, M2. Now M2, remember it was 11.3 grams in 300 seconds. But for us we want per second. That is why we divide by 300. Then why do we multiply by 10 to the power negative 3? It is to convert the grams to kilograms. Then also minus M1, which is this, grams in 300 seconds, so change to kilograms by multiplying by that, divide by 300 to get per second. And that is outside. So L is the only unknown. Simplify and make it the subject, and that's what they wanted. So when you go back to the question, you have got the specific latent heat of vaporization, but they said they want calculate the power of the heater required to evaporate 3 grams of water in 2 minutes. So for 3 grams of water, it implies that the mass per second will be 3 grams convert to kilograms to give you that, then divided by the 2 minutes, with the 1 per second, so 2 minutes to convert minutes to seconds, you multiply by 60. So it gives you this kilograms per second. That is mass per second. Okay. That means that for the if I use this third set and the first set, I'll be able to come up with this. So I'm just getting it from here. From this part I'm replacing I2 V2 and M2 with I3 V3 and M3, where M3 is this one, I3 V3 is the new power. So I'll come and substitute, leave this one as it is because they want the whole of it. Substitute for I1, V1, M3, M1, and specific latent heat of vaporization. So here my aim is to make this one the subject. So simplify and make it the subject, and that will be the power required. Then question 3 came from UNEB of November 1998, paper 1, question 5D, and it says, when electrical power is supplied at a rate of 12 watts to a boiling liquid, this kilograms evaporates in 30 minutes. On reducing the power to this mass of the liquid evaporates in the same time. That means it also evaporates in 30 seconds. Calculate Roman 1, the specific latent heat of vaporization of the liquid, and Roman 2, the power loss to the surrounding. So let capital H be the power loss to the surrounding. Therefore the first set gives you that, and the second set gives you that. I believe by now you know where these equations come from. This is the electrical energy supplied, rate, latent heat, heat loss. So when I subtract the two equations, I'll come up with that. The aim is to eliminate the heat loss to the surrounding. Then I can substitute. Now here I'm substituting. This was grams, multiplied by this, make it kilograms, and divide by this to make it per second, because it was 30 minutes, so we have to change the 30 to seconds. That's why I multiply by this 60. Then you simplify and make L the subject. That was Roman 1. Then Roman 2, they want the power loss to the surrounding. They want the value of H. So it means that here, from either equation 1 or equation 2, if I use equation 1, I'll come and substitute for P1, M1, L, and H. So H is what I want, therefore I have to make it the subject, and that will be the answer they wanted. Question 4 came from UNEB 2016, paper 1, question 5D, and it says, in an experiment to determine the specific latent heat of fusion of ice, a heating coil is placed in a filter funnel and surrounded by lumps of ice. The following two sets were obtained. So we have two sets still, V1, I1, M1, V2, I2, M2. So calculate the specific latent heat of fusion of ice, and Roman 2, the energy gained in the course of obtaining the first set of readings. Now here, in the previous question, that was question 3, we are dealing with latent heat of vaporization. And also in the previous question, that is question 1, 2, 3. But now question 4, it is latent heat of fusion. So what happens to the heat gained? So now we no longer talk about heat lost, we talk about heat gained from the surrounding. Therefore, when you are quoting the equation, you shall come and say that, first of all, let L be that, and H be the heat gained by ice from the surrounding. Now it is no longer heat lost to the surrounding, it is now heat gained from the surrounding. So what does that mean? It means that by conservation of energy, we are going to change a little. Previously, when it was heat lost to the surrounding, this we would have put it here, this side. But now because it is heat gained from the surrounding, we put it on the side of electrical energy supplied. So at this side we only put latent heat. Therefore it will now be, because it is now not rate. If it was rate, it would have been IV, but now it is heat, so that is why there is IVT plus H equal to, like I've said, we use small h if it is just heat. If it was rate of heat, it would have been capital H. So IVT plus H is equal to ML. That is the first set. What about the second set? I2V2T plus H equal to M2L. Then subtract the 2 to eliminate this H. Then you substitute. And when you substitute, it is only L which is unknown. Therefore, you can easily make it the subject. So simplify and make L the subject. That will be the latent heat of specific latent heat of fusion. Then for Roman 2, they want the energy gained in the course of obtaining the first set of readings. So from equation 1, it implies that you come and substitute for L. Substitute for I, for V, for T, and then H is what we want, M1 is that, then L is that. So make H the subject, and that will be the answer they wanted. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on thermal conduction. So if you have not yet subscribed, please click on the subscribe button below this video such that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp such that you can all benefit as a family.